So the Soyuz is a good. I mean, I would definitely prefer to ride on the Soyuz than the space shuttle. You have an escape system on the Soyuz. Oh, and then of course on reentry, a capsule, a blunt body reentry capsule, can be designed to be naturally stable, so that even if all the control systems fail, that you're just lights out, dark, everything's it's naturally, it's like a shuttlecock. It's naturally stable on reentry, and you don't have to do anything there, and you can just manually pull the chutes or something like that. So, in fact, that's happened on a couple of Soyuz flights where they've had control system failures. If that had been the shuttle, it would have been curtains. But because it's naturally stable, you don't have to worry about that. And then because you've got that blunt body reentry, the heat shield is much more robust because you've got this really big radius heat shield instead of these sharp radius wings. So it's really a much safer design. I believe there's never been a fatality on the Soyuz, which has been going much longer than the shuttle. Made many more flights. So I don't like wings for things that go to space where there is no air. Let me correct a misconception. A blunt body, sort of a capsule, gumdrop style thing, is a controlled landing. In fact, because you still have a lift vector, so you use offset center of mass to create a sort of a tilt in the capsule, and that actually creates a lift vector. And that lift vector would typically be a lift of a drag of 0.2 to 0.3, but that's plenty enough to steer you where you want to go. And in fact, even in Apollo, when they didn't have GPS and they were really dealing with very primitive electronics, their landing accuracy was a 1 mile radius. And of course, if you can get much better than that with GPS and all that other stuff. In fact, the only error is the wind drift. That's really the only meaningful error. And if you do steerable chutes, or put some like a little propeller that popped out or something like that, you could drop the capsule on the numbers on the runway. Just like a parachutist can steer their flight down to a very accurate location. And then you could, I think you just sort of like flare it just before you get to the bottom, just like a parachutist, and there you are. Well, Mars is the only place where we could really create a self-sustaining civilization on a planet scale. If you look at the various planets, we've got Mercury's too close to the sun. I mean, the rocks melt on Mercury, and then Venus is still pretty hot. It's several hundred degrees, and it's high, and the atmosphere is high pressure, and it's acidic. So Venus would be very challenging. And then Mars obviously is on the other side of Earth, and it's colder than Earth, but the temperature on Mars actually gets above room temperature on Earth on a hot day in the summer. And you could warm Mars up over time with greenhouse gases, and kind of the opposite of what we're doing on Earth. Mars's atmosphere is primarily carbon dioxide, which shows you how long, I mean, it's been there for 4 billion years, shows you how long carbon dioxide lasts. So when I started SpaceX, it was actually, I thought the most likely outcome was that we would fail. In fact, I thought that was really very likely that SpaceX would fail. So it wasn't really with the expectation of success that I started the company, obviously. But what gave me a clue that we could make a significant breakthrough was looking at the cost of a rocket, and instead of looking at it with reference to what other rockets had cost in the past, I said, okay, well, what is a rocket made of? What are the material constituents? What metals, carbon fiber, what are the various materials that constitute a rocket? And if you had a pile of those materials arrayed before you and you could wave a magic wand, what would that rocket cost to build? And that is a remarkably small number. It was maybe a few percent, or 1 or 2% of what rockets actually cost. So clearly, people were doing something silly in how they were putting those materials together. And so just by eliminating those sort of foolish things, we were able to make a rocket for much less. And then it wasn't obvious to me that one could achieve full and rapid reusability. In order to achieve that, everything has got to be done super well, every aspect of the vehicle. There's G-loading, max G-loading, and dealing with worst-case abort conditions and that kind of thing. It's just, all those things we're designed to meet. There's one key development item that we need to finish, which is the escape tower, so that we have a launch escape system. In case something goes wrong with the core booster, it can carry the capsule to safety. It's also something they had during the Apollo era, but didn't have that for the space shuttle. And really the two weak areas of the space shuttle, and the two most dangerous periods for a manned vehicle are during the ascent phase and the descent phase. There are fundamental architectural flaws with the shuttle approach. One is on the ascent phase, there is no escape system. They decided they didn't need an escape system because the shuttle would never fail. Really? We're like, wow, okay. So there's no escape system if anything goes wrong on the ascent. And then on re-entry, particularly the initial part of re-entry, which is the high heating point, because it's not a naturally stable vehicle. You've got to have control surfaces and wings. So it has control surfaces and wings. So if anything happens with the control system, so any the electronics that don't work or malfunction, or there's a hinge that isn't working properly in one of the control surfaces, it's not naturally stable. It has to be controlled, and then the heating rate goes with the square of the radius of whatever you're dealing with. So if you've got a wing leading edge that's got a very, effectively got a sharp radius, you have a very concentrated heat, which limits the material choice to some very brittle materials. In fact, it'll only work for Earth orbit reentry. If you come in at a higher velocity than low Earth orbit velocity, there's no material known to man that can withstand it. So actually, for like the moon, you couldn't use a winged vehicle. It's impossible. It's not like, if you think of the Apollo era, okay, they had airplanes back then. It's not like, oh wow, wings, what are those things? The designers of Apollo, von Braun and the others, were very familiar with aircraft. If they thought wings made sense, they would have said, let's put wings on this thing. They don't. When it comes to space, wings are dumb. Just as you don't make an airplane look like a boat. Like the Saturn V, although it had 5 engines on the first stage, also had 5 engines on the second stage, and then 1 engine on the third stage. So it was actually an 11-engine rocket. Falcon 9 has got 9 engines on the first stage, 1 on the second stage. So it's actually one total of 10, so 1 less than a Saturn V. And the advantage of the 9 engines is that you can lose an engine at any point, including immediately after liftoff, and still complete your mission, which was not true of the Saturn V. The thrust weight of the Saturn V was about 1.15, so you actually had a very dangerous point immediately after liftoff, where you could potentially subside if you had an engine failure within the first few seconds. With rockets, because you're taking off vertically, it actually for the first stage, it actually, the initial boost stage, points you towards having more engines, because if you want true engine out capability, because you always have to have a thrust weight greater than 1, otherwise you're coming back. Whereas in aircraft, you can have a thrust weight of much less than 1 and still be okay, because you can sort of glide and reduce your climb rate and that kind of thing and still be okay. So it actually it does push you to have more than say, like 747's got 4 engines, but the equivalent for a rocket would be some number greater than 4. And maybe it's not as high as 9, but we needed 9 to achieve the payload requirements that our customers wanted. And as long as you're very careful about ensuring that the problem with one engine cannot cascade into problems with another engine, more is actually better. Google operates with tens of thousands of computers rather than a few giant mainframes. So if you think 9 engines is bad, try 6,831 cells. I think it's possible. I think we could make it work. Like, think of it this way: if we're not violating any laws of physics, it's difficult but achievable. and I think we should really try our hardest to make it happen.